yeah, just a recap regarding what we went over on Tuesday is that we have a z or a zi that follow a standard normal distribution. So with a mean 0 and the variance equal to 1. And then if we have k copies of them, so from z1, z2, all the way to zk, and then we write identically or independent identically distributed that follow the same standard normal distribution, then we say that the following construction from 1 to k and then zi squared following a chi-square distribution with degree of freedom k. So last time we used the moment generating function to show that the sum of zi squared following a chi-square distribution. And then we also point out that the chi-square distribution is essentially a special case of a gamma distribution. And let's see what is the parameter that I put down. So alpha is just the degree of freedom k over 2, and then beta is equal to 2. So whenever if you want to use or to find the density function for the gamma for the chi-square distribution, you can always just use the gamma distribution and then plug in the corresponding alpha and beta to get the density function for a chi-square distribution. Okay. Furthermore, we also talk about the following construction. So for a z, random variable z that follow a standard normal again, and then for a random variable v such that v following a chi-square distribution, or maybe let me write it more. So v following a chi-square distribution with degree of freedom k, that you can also construct it in this way. And then if you use the v divided by the constant k, which is the degree of freedom for this chi-square random variable, and this is essentially a t distribution with degree of freedom k. So this is another distribution that we can derive from both the standard normal distribution and the chi-square distribution. Okay. And then in today's lecture, we are going to talk about the F distribution. Okay. And the F distribution is also related to the chi-square distribution, and then it is related in the following way. So let U1 following a chi-square distribution with degree of freedom m, and then let V, let me use U again just to avoid the confusion here. So let U2 follow another chi-square distribution degree of freedom n, and then you can so let's say if you draw a sample from U1 divided by m, and then if you have another U2 divided by n, so if you're doing in this way, then you are essentially constructing a F distribution or F random variable from a F distribution with 2 degree of freedom. The first one is m and the second one is n. Okay. So here, as you can see that we started with the standard normal, the univariate case, standard normal from a 0 and 1. When you sum over k copies of the zi squared, you will get a chi-square distribution degree of freedom k. And then if you use a normal divided by chi-square, you will get a t distribution. And then if you have a ratio of 2 chi-square distribution with different degree of freedoms, you will obtain an F distribution. And all these 3 or 4 distributions, including the normal, they are extremely helpful for hypothesis testing, depending on what is your research question or what is your hypothesis at hand. Yeah. So yeah. And then these are how you can construct these important random variables just from the normal distribution. Yeah. And then in today's lecture, I'm first going to talk about, again, using the method of transformation to derive the density function for the F distribution. So similar to what we see last time, where we use method transformation to get the t distribution. So in the following, or in the first half of the lecture, we are going to use the method transformation from the 2 gamma distribution, or the chi-square distribution, to obtain the density function of a F distribution. Okay, so maybe sit down is better. Any question or comments up to this point? Okay, then let's begin. And also, these can serve as your, so deriving the t density function and the F distribution, they can all serve as a very good exercise for your practice on the method transformation, because we are just using the method transformation again and again to derive what we really want. Okay. So here, let me write down the examples. So you can always use all these examples. So from the first equation, and then you can do it from scratch to derive the result, and then as a practice for your either homework or midterm. Okay, so what we said is that, let me write down again, U1 following a chi-square degree of freedom m, and then U2 following a chi-square degree of freedom n. Also, another thing is that when you do all this construction, there's another important thing I think I left out, is that Z has to be independent of the chi-square when you construct the t distribution. And also, the U1 has to be independent of U2 when you take the ratio. So all these, also here you have the IID condition. So all these things must be independent for this ratio Z over V, or this U1 over U2, to construct the corresponding t distribution and the F distribution. If they are not independent, then they do not follow the t, or they do not follow the F anymore. Okay. Okay, then back to our exercise. U1 and U2 are independent. Okay. So these are from the chi-square distribution, and what we want is the F distribution. So again, we are going to write some transformation from these chi-square random variable. So let's first define W1 as U1 over U2. And let's define W2 as U2. So you can consider this as your function G, that input U1, U2, you should get the W. Okay. And for the next step for the method transformation is to get the H inverse. So here, you can write U1, it's equal to W1 multiplied by U2, where U2 is W2. So you have U1 equal to W1 multiplied by W2. So that is your function H1 inverse. And then for the H2 inverse, you can just have U2 equal to W2. And then if you want, you can also write 0 multiplied by W1, just to make this as a H inverse, a function of both W1 and W2. So you can always adding a 0 multiplied by the things that it does not appear over there as a function of two parts. And then on the top, this is just your function of G, U1 and U2. Okay. Once we have both G and the inverse function, the next step is to find the Jacobian. So again, either you use J1 or J2, depends on which one is easier for your derivatives. So in our case, we are going to use J1. Okay. So in our case, we have a two variables, so our Jacobian matrix should be a 2x2 matrix. Okay, let's first write down the determinant. And then for J1 is the original over the new variables. And then for J2 is the other way around. So you can always using to resort to the formula to see, or you can just copy the formula to get the result. And then du2 over dw2. Okay, so that is our Jacobian matrix. And then to find the determinant. And next, we just need to calculate the derivative and then to get the corresponding entries for this 2x2 matrix. So du1 over dw1, so from here, we know that this is, w2. Okay, du1 over dw2, and this should be w1. Okay, and du2 over dw1. So there are 0 copies of that, so you have a 0 here. So that also means that if you take the off diagonal, the product of the off diagonal, you will just have a 0. So maybe that could also serve as a reason why we want to choose J1 to ease our computation, as there will be a 0 showing up. Okay, and then du2 over dw2. So just 1 copy of that, so you have a 1. And then the determinant. So that you have the product of the diagonal minus the product of the off diagonal. So you only have a 1 copy of w2, and that will be your J1 here. Okay, once we have the Jacobian, we can revisit the density function for the u1 and the u2. And then we are going to make the substitution for u1 and u2 by replacing it with w1 and w2 to change the density function from u1 and u2 to the density function of w1 and w2. That is our goal here. Okay, so first let's write down the joint distribution for our original random variable u1 and u2. And because they are independent, so this is just the density function for u1 multiplied by the density function of u2. And then each of them following a chi-square distribution, or in other words, they follow a gamma distribution. So we can use the gamma density function to write it here. So we will have u1 raised to the power of alpha. So here, so maybe let me write it so maybe let me just squeeze in here. So for the chi-square, you should have, for the u1, you should have m over 2 and then beta equal to 2. And then for the u2, in terms of the gamma density function, you will have n over 2 and then beta equal to 2. Okay, so these are our alpha and beta here. And then these are the alpha and beta we're going to use in the density function. So so the density function, so the alpha and beta are here on the upper right, and I'm going to write it in the bottom here. Okay, so for u1, we have u1, and then alpha minus a 1. So alpha for u1 is m over 2 minus a 1. And then we have a exponential function of negative x over beta. So in our case, x is u1 here, and then beta is 2. And then for the normalizing constant, you will just have the gamma function of alpha. So alpha again is m over 2, and then we will have beta raised to the power of alpha. So beta again is 2, and then alpha is m over 2. Okay, so this is the density function for u1. And similarly, we have the following for the u2. So u2, n over 2 minus a 1, and then exponential of negative u2 over 2. and then you have a gamma function of n over 2, and then 2 raised to the power of n over 2. So here we are just using the gamma density function, but using the alpha and beta from here, and then by rewriting the x by u1 and u2. Okay, and the reason for that is that they are independent, so you can write as the product of the margin. Okay, so this is the density function for u1 and u2, but what we really want is the w1 and w2. So now we are going to make the change. So So now we are going to replace u1 by the inverse function, or by the construction. So u1 is equal to w1 and w2. So whenever you see a u1 here, you just replace with w1 and w2. So w1, w2, and then together raised to the power of m over 2 minus 1. And then you have an exponential of negative. U is w1, okay, yeah. So w1 multiplied by w2 over 2. And then for the normalizing constant, they stay the same. So 2m over 2. Okay. And then let's replace u2 with w2. So we have w2 raised to the power of n over 2 minus 1. And then we have an exponential of negative w2 over 2. And then the normalizing constant stay the same. So n over 2, and then 2 raised to the power of n over 2. Okay, so now we have to make the change for u1 and u2, and we change it to w1 and w2. So is this formulation complete or not here? Or are we missing something? Or what are we missing here? The Jacobian, yes. Yeah, I just want to make sure that you guys still remember there's a third component. So yes, nice. Okay, so we need to multiply by the Jacobian. So in our case, we are using the J1, so there's no need for the absolute value. And J1 is W2. And then don't forget the absolute value, and then there's no inverse. Okay. Then the rest is just simplifying this expression here. So yeah, so one thing like what we did last time is that we can group the normalizing constant first. So we will have a gamma of m over 2, and then gamma of n over 2, and then 2 raised to the power of m plus n over 2. And these will be in the denominator. Okay, then we are going to group the things in the numerator. So here we have W1 raised to the power of m over 2 minus 1. And then we have two parts that involving W2. So we have, or actually 3 parts that involving W2. So we have W2 of, let's see, how should we group it to make it easier? Okay, so maybe let me group it in this way. So m plus n over 2. So this is the first m over 2 is coming from the first density function, so from here. And the n over 2 is coming from here. And then they all need to minus a 2 because of this minus 1 here and the minus 1 here. But you have an additional copy from the Jacobian, so you need to plus a 1 here. So you have the m over 2 here minus a 1 and n over 2 minus a 1, but you have another copy of W2, so you plus a 1. And then we can group the exponential term. And then we are going to group the exponential term in the following. So negative 1 over 2, and then W1, W2 plus a W2, because we put the minus sign in the front. So we will have W1 plus 1 together multiplied by W2. Okay. So this is the joint density function for W1 and W2. But what we want in the end is the marginal for a random variable, or in our case is W1, because W1 by construction is the ratio U1 over U2, which is because we want to construct the W1 in this ratio because of this one. This is the construction for a F distribution. So that's the reason why we set up W1 as U1 over U2. So our goal here, so our next step is to find the marginal distribution for W1 to get the marginal distribution for this ratio. And then in the end, we will take care of this m or n over m in the end. And that will give us the final density function for this particular ratio here. Okay. So our goal is to integrate over W2 to get the marginal of W1. So specifically, W1 is equal to the integral for the joint, and then dW2. Okay. So that means for the next step, we are just going to take the integral with respect to W2. So everything that involving W2 should be pushed inside the integral. Okay. So now let's regroup this formula here. So we will have the same normalizing constant for the n over 2, and then 2 raised to the power of m plus n over 2. Everything here for that. And then let's see. Okay, so I'm going to also leave the first W1 outside the integral. So m over 2 minus 1 from here. And then I'm going to bring this term, or the remaining term, inside the integral. Okay. And the reason for that is that this is also a kernel function for the gamma distribution. So let me first write it down. And then dW2. So now, as you look into the integral, this is a kernel function for another gamma distribution. And the kernel function for that particular gamma is with the following parameter. So alpha is, let me write it here. So this alpha here for this kernel function it's m plus n over 2, the one without the minus 1 here. That's your new alpha. And then for the beta, is the negative of your random variable divided by something, and that something will be your beta. So in our case, our beta will be the 2 from the denominator, and then W1 plus a 1, and then taking the inverse, because we need the W2 divided by beta to get this one here. So this will be your beta. And then as we recognizing that this is a kernel function for a gamma distribution, and then when we integrate the over the kernel function, we will get the normalizing constant part for of a gamma distribution. So just to write everything completely, we have m over 2 n over 2 that's that, and then W1 m over 2 minus 1. Okay, and now let's integrate the kernel function to get the normalizing constant. So we should have something like a gamma function of the alpha. So the alpha is m plus n over 2. And then we will have the beta raised to the power of negative alpha. So we will have 2 raised to the power of alpha. So m plus n over 2. And then the W1 plus 1, and then raised to the power of negative m plus n over 2. Okay, so then as you can see on the last equation here, only involving W1. So now it's a marginal distribution for the random variable W1. But this is still not the density function for a F distribution, because we only take care of the ratio of U1 over U2, but we have not yet take care of the coefficient that's divided by m and divided by n in this construction. So we need to use also the change of variables to take care of this coefficient for n over m. Does that make sense? So what we want is the density function for this one here. And what we get so far is the density function for this U1 over U2. So to get the final density function for this expression, we also need to include the n over m, because they're in the denominator. So the n over m inside the density function to claim that that is the density function for an F distribution. Okay, so this particular example here, we're not only using the method of transformation, we're also using the change of variables, which is what we introduced before when we introduced the method of transformation. Okay, so just to remind you what is the change of variable is the following. So let me just write down, and it's also in your notes from last week, which is saying that the P of y is equal to the P of x, or the density function, and then you will need to use the H inverse for the y, and then d of dy, the H inverse y, the absolute value. So this is the univariate case that we talk about before we talk about the bivariate case where we use the method of transformation. So I'm sure this is also in your notes, and then this is the thing that we are going to use it again. So in this examples, we have using two techniques that we talk about to complete this examples. Yeah. Okay, so now to complete our density function, let's define another random variable u, which is equal to n over m w1. So here, this w here, this w that we introduced in the end will be equivalent to u1 over m and then u2 over n, because we are multiplying a n over m in the front. So this density function for the m, not the m1, is the one that we really want for this ratio. Okay. Oh. Okay. So now this is your function g of w1. And what we want is w1 equal to the h inverse of w. And then what we have, or what we need to do is just multiply by m over n on the other side, so w. And this will be your h inverse y. Or in our case, our y is the w here. Yeah, so that is your h inverse. Okay, then we just need to calculate this derivative, and don't forget the absolute value. So the derivative of h inverse w dw is just m over n. Okay. So, yeah. So in other words, we just need to multiply by m over n and then an absolute value in this formulation. But let me write it out more clearly, because this is a random function for w1, and then we are going to change the w1 to w. Okay. So here should be our final answer for these examples. So the density function for w. So just to make it clear, this is the density function for w1, but we change w1 to this thing here, m over n w. So here our final result is a density function for w only, not the w1 or w2, it's just the w. And then again, just plug in. Let me see if I can just copy. Can I do that? I can copy it. And then how can I? Nice. Okay. Yes, okay. So all we need to do, just rewrite all the w1 to the things that we construct. So w1 is m over n w. So that's the first w1 that we replace. There's another w1 here. So m over n w. Okay, so now, as you can see on the right hand side, it's only involving w. So no more w1, w2, or u1, u2. And just for one final simplification, you should get the following. So m plus n over 2. And this step, it just depends on how do you like to group things, or it's really up to you. So here I'm just grouping all the gamma function together, n over 2. And then, oh, this 2 cancel out. You have this one in the denominator and this one in the numerator, so it cancel out. And then, oh, so again, let me ask, am I missing something here for this one? This time I make a mistake here. So what mistake did I made here? I forget to time the Jacobian thing, right? The thing. Yeah. So there's another copy of m over n. Okay. Because I often forget, and then it will give you the wrong answer. So I always want to remind you as well. Always don't forget there's a third part. I remind this again and again, and then today I also just forget. So yeah. So there's additional copy. Always don't forget when you make the change to the variables, there's an additional copy from the Jacobian or from the change of variables. Yeah. So that means this copy of m over n from the Jacobian, or for the univariate case, will cancel out with this copy for the m over n. So you should have m over n raised to the power of m over 2. So no more -1 here. And then the rest is just the w raised to the power of -m plus n over 2. And then the m over n w plus 1 -m plus n over 2. Okay, so if you miss the last term here, you will not get the correct result, and then something will break, let's say in your research. So always make sure to have the complete component in your formulation. Yeah, but in our examples, just to summarize, the F distribution can be constructed from 2 chi-square random variables, and that has to be independent. And in this examples, we practice again by using the method of transformation to rewrite the joint distribution starting from U1 and U2 to the joint distribution of W1 and W2. And then in the end, we use the technique for the change of variables to change the marginal density function from W1 to the marginal density of W. And this is the probability density function for F distribution with the corresponding degree of freedom m and the n. Okay, so I think this will serve as a very good exercise to practice all these techniques that we talked about from last time. And also with these techniques or this practice, we introduce all these new distribution, the standard normal distribution, the chi-square distribution, the t distribution, and the F distribution. And then they are very useful for your research, for your, in particularly hypothesis testing. Yeah. Any question or comments before we start another topics? Okay, if not, then for the remaining of the lecture, we are going to talk about multivariate normal distribution. Okay, so far up to this class, what we have been talking about are all univariate distribution. So we have been talking about I think starting from week 0, we use a Poisson distribution for a discrete case. We talk about exponential distribution. We also talk about binomial distribution and also gamma distribution. In the homework, you also see, or from last time, you also see the beta distribution. And also normal, and then all these t, chi-square, and f distribution. So all these distributions so far are all unit variant for one random variable, or for, let me write, for x in like at least a real value, or a scalar. Let me put it. Yes, I think scalar would be a better word. Okay. They're all scalar. So in the rest of the lecture, we are going to talk about x, or the random variables, that they are random vectors. So let's say from 1 to n, so for example, particularly in the normal case, this is in Rn. So this column vector that we are going to denote it as x will serve as our random variables. But this random variable consists of like n elements in there. So this is referring to the multivariate case. So previously we only talked about the scalar. You can think about just the x1 here. That's for one element. But right now we're going to talk about multivariate case. It's just a vector. So everything is going to involve vector and matrix from now on, or for the rest of this class. Yeah. Okay, so let me use, okay, so maybe, yeah, so let me just, yeah. Okay, so in the context of normal, I'm going to use this random variable y here. I'm not sure how do you guys want it, but here I'm referring to a vector. So usually in the textbook, you will see is basically using a bold font, or people sometimes like using a like an underline, just to refer this is a vector, not a scalar anymore. So yeah, so it's up to you. How do you want to show that this is a vector, not a scalar? So usually people use both font and or underline, but for the simplicity, maybe I'll just not do that, just for the make it clean. Yeah, but just to let you know that we're talking about vector, not scalar. Even I might write the same way. Okay. So this y have this y1 all the way to, let's see, just use n, arbitrary number n. Yeah. We'll have this vector n. And then we write y following a multivariate normal. So sometimes people using a subscript here just to denote the dimension for this random vector. So in our case, I can put an n here just to refer that this is a vector of n elements here. Okay, and then you also have a mean vector. So this is also a vector in Rn. So this is also in Rn. And then you will have a capital Greek letter sigma matrix. And this is in Rn by n. So essentially you have a column vector, and then a matrix. And just to make it more precisely, so you can write the mu also as mu1 all the way to mu n. And then for the sigma matrix, which is a n by n matrix, you can also write it more explicitly. So this is the sigma 1 square, sigma 1 2, sigma 2 1, and then you have sigma 2 square all the way to sigma n1, and also to sigma 1 n, and then all the way to sigma n square. So this matrix will serve as this capital sigma matrix here. Okay. And then for each of the elements, you can think of it, this is the variance for the for y1 or y sigma I for yi. And then sigma ij is just the covariance between the yi and yj. Yeah. But just to emphasize that this is a column vector Rn, and then if you want, so n by n, and then also they have to be should be positive, yes, because we're not talking yeah. And also sometimes you will see people writing correlation sigma 1 sigma 2 for sigma 1 2, just and this is the correlation that we talk about very early in the video of week 0. We talk about the correlation. Yeah. So sometimes people write in this way, but here I'm just using like a to show or to use this like a shorter notation for the covariance between the first between ij variables from the column vector y. Yeah, so in this case, it's just the covariance for 1 and 2. And you can using arbitrary sigma ij for ij elements. Yeah. Okay, so that's that. And then let's write down the density function. So so the density function now is going to be in a vector matrix multiplication form. So here we will have the 2 pi again, but raised to the power of negative n over 2. And then you will have the determinant of this sigma matrix, and then raised to the power of 1/2. And then you will have the exponential term for negative 1/2, and then y minus a mu. So y is a column vector with n elements. Mu is also a column vector with n elements. And then you will need to take the transpose. So are you guys, because last time someone told me you guys are very familiar with the matrix vector things. So are these notation like very familiar, or do I need to talk about them anymore, or are these notations so far are there any question regarding the notation, like transpose or yeah? Sorry, can you say that again? Talk more about those operations. To go over it.
Just like when we use notation, like matrix operations, just so it's it would be helpful to say what it means.
Good. Thanks. Yeah. Okay. So for here, when you take the transpose, so it also depends on depends on vector and the matrix. So for a matrix, so yi for yn, this is your y. Okay, so y transpose here. So this is a n by 1 column vector. And when you take the transpose, this will become a row vector. So y1, y2, all the way to yn. So this is what I will be using for the transpose here. And then for the matrix version, so let me use, how about A? Okay. So A in the matrix form. So A, okay, so I'm going to use single index, although I just want to focusing on the difference. So maybe I'll use single index A1, A2, A3, and the A4. Okay. So when you take the when you define matrix A, a 2x2 matrix in this case. Okay, because if you talk about notation, there are a lot to talk about case by case. So for A inverse, for this particular square, and they are not necessarily a symmetric matrix, you will have the following. So A1 and then A4 stay the same. But here you have A2. When you take the transpose, essentially just flipping the matrix from the diagonal matrix, from the diagonal here. So then you will have the A3 and A2 change the position. Okay. And when this is a symmetric matrix, then that means you will have the same thing, because A transpose is equal to A. That is the definition for a symmetric matrix A. Okay. So then when you rotate this matrix from the diagonal as the axis, then you essentially still get the same matrix. So you have A transpose equal to A. This is only for symmetric matrix. But if A is not symmetric, then you will have the A3 here. Okay. And then when you take the transpose, you have A3 on the top and the A2 here. And then additionally, when you have a non-squared matrix, let's say here you have like a n by p, and let's denote this is matrix B. Okay, then B transpose is going to be P on the rows and then N on the columns, and this is defined as B transpose. Okay. So these are some operation. Is it good for now? Okay, perfect. Thanks for the comment. So yeah. And then just complete our density, multivariate density function. So that is the transpose operation. And then you will have the sigma matrix inverse, and then y minus mu, closing the parenthesis. So this is the density function for a multivariate, or more specifically, n-dimensioned normal random variable. So just to check the dimension here, this is a scalar, so this is a 1 by 1, or well, scalar you can always consider as a 1 by 1 matrix, or 1 by 1, or a vector with one element. So this is a 1 by 1. And the sigma matrix is n by n, but the determinant returns a scalar. So again, you will get a scalar. Okay. So yeah, let me write 1 by 1. Okay. And then negative 1/2 raised to the power. And then the last term here, this is a n by 1 minus a n by 1. You should get a n by 1. And then sigma matrix is n by n. When you take the inverse, it's still going to give you a n by n matrix. And then here, it's going to be a n by 1 minus a n by 1. So you should get a n by 1. But don't forget, there's a transpose here. So you will have a 1 by n. When you transpose a column vector, when you take the transpose, it will become a row vector. So you have a n by n, a 1 by n. And then here, you will have a n by n and a n by 1. So we have a matrix, we have a vector matrix multiplied by a vector. We have a row vector 1 by n multiplied by a square matrix n by n multiplied by a column vector n by 1. And in the end, you should get a scalar. So for matrix vector multiplication, make sure that all the dimensions should be lined up. So here, the multiplication operation is only valid when the adjacent dimensions are equal. Otherwise, the operation will not be performed. So we have 1 by n multiplied by n by n, so that's a valid operation. we have a n by n multiplied by n by 1, that's also a valid. And in the end, you should get a 1 by 1, the dimension from the beginning to the end as your dimension for the final result. So you will have a scalar multiplied by negative 1/2 using the exponential, another operation. In the end, you will have a real value 1 by 1, or you can write R1, or people just write R. Okay. Any other comments and thoughts or anything for clarification? Okay, yeah. So this is the density function for a multivariate normal. And for the particularly y, follow a mean, mu, and the sigma covariance matrix. Okay, then there's always a special case, which is the multivariate standard normal. So we write it as a normal. You can also write it as a dimension n, 0, and then identity. So I usually just put n also in the identity matrix here. Okay, so this z here, again, it's z1, z2, all the way to zn. Okay, also n by 1 column vector. This mu, which is a 0, it's a 0 column, 0 vector, column vector. So you have 0, 0, and then all the way to 0. And there are n of them. So this is a 0 vector. And then for the identity matrix here, let me put down, so this is n by 1, this is n by n. So for the identity matrix, it's referring to the following. So you have 1, 1, all the way to the n entry. And then for the remaining, they are all going to be 0. And this is the identity matrix with n. So identity matrix is always referring to that the main diagonal, they are all equal to 1. And everywhere else should all be 0. Yeah. And then anything multiplied by identity should give yourself. If you have a vector, maybe I should not use beta for now when we talk about linear regression. Oh, okay. So what else? Okay, then I use mu for a vector. So this is a n by n multiplied by n by n. You will have n by n. And then let's write identity. So this is n by n, and then n by 1. So you can only multiply vector matrix or matrix matrix or vector vector where the dimension is they are matching. So we have n by n multiplied by n by 1. You will also have a mu itself, and this is n by 1 again. Okay, and that is the things for identity. When you multiply by identity, you will always get yourself. So A identity equal to A, or IA equal to A, and then I multiply by a vector, you'll get your vector yourself. Okay. That's that. Okay, yeah. And then you can write down the density function for a standard normal. If you want, you can also just plug in the corresponding component to this one. So the sigma matrix become an identity. This y become a z, the mu become a 0. Also same thing here. So that means the density function for z is going to be 2 pi negative n over 2. Determinant of an identity matrix. So in this special case, determinant of the for an arbitrary dimension identity matrix will always be 1. so that you don't need to consider about that. But I'm going to put 1 here to refer to the determinant. When you plug in the sigma matrix as identity, it will become a 1. So usually people you just don't see a determinant for a standard normal. And then you will have an exponential. The 1/2 is still going to be there. The z, which is a column vector, minus a 0 vector, so it's still going to be z. And then altogether you have a transpose. And then the sigma matrix is just identity. So if you multiply it to there, you will still get yourself. So I'm not going to write identity there. So the inverse of the identity is also identity. So if you put the identity there, it will just be itself. So that I'm not going to put identity there. And then another copy of z minus a 0, which is also a z, closing that. So this is the density function for a multivariate standard normal distribution. So just to check the dimension, the first term is still going to be scalar. This 1 is also a scalar. Z is an n by 1 vector. Taking the transpose, you will have 1 by n. And then you multiply by another n by 1, you will get a 1 by 1, which is a scalar. So everything here in this line will give you a scalar. Okay. Now we have talked about multivariate normal density. So the next subtopic, is the joint moment generating function. So whenever you have a distribution, you can always talk about the moments. And in our case, the moment generating function is no longer a scalar version. It's also going to be a matrix vector multiplication version. Okay, so let me put it here. Okay, so let's define also a vector for t. It's a vector t1 all the way to t. Since we use n, then let me just use n then. So now t is no longer a scalar. So in the univariate case, the moment function t is a scalar. And in our case, for the joint density function, it's going to be a vector. So here, let me use x now. So x1 all the way to xn. And then the joint moment generating function is going to be the following. So here x is a vector or a multivariate random variable with the same definition. So let me put definition here. Okay. Again, it's the expected value. And then same thing, e raised to the power. But here we have t, which is a vector, transpose multiplied by x. Okay. So in the univariate case, m of x t, you will have e tx. So t is a scalar, x is a scalar. That's a univariate case. The only difference here is that t is a n by 1 vector. X is a n by 1 vector. You need to take the inner product. Okay, so let me give you a brief comments on the inner product. So t vector t transpose multiplied by x. This is equivalent to t1, t2, all the way to tn. After the transpose, so t is a column vector. When you take a transpose, it becomes a row vector. And then you multiply by another column vector. And this is sometimes people call inner product or a dot product. And if you want to make it a scalar version, you can have a summation operation again for I from 1 to n. And then this is just a ti, where this one here is a scalar. And then multiplied by x, xi. Okay, yeah. So this is the scalar in the corresponding, let's say, t2 multiplied by x2. Okay. So, like what I said on Tuesday, matrix vector multiplication is essentially a summation of scalars. Although they're just like you have to write it into in a two-dimension things, or even higher dimension, like a location, one entry, two entry, two entry, that kind of things. But in the core, they are all just summation operation. So for example, this inner product, or the T transpose X, it's just that, and that it will return a scalar. Okay, so let me use in. So this is also a scalar. Okay, so that's for the inner product. So now let's talk about homogeneous function for standard normal. So E of ET transpose Z. And then this is the expected value for E of T1 multiplied by Z1 plus all the way to Tn Zn. Okay. And then because they have the identity covariance matrix, so that all the zi's here in this column, they are IID, the scalar version 0 and 1. When you put them together, this is a column 0 and an identity matrix. But when you're looking at the individual entries, they are just IID 0, 1. And then they're independent. So that's why, let me put independent here. You can write it as Z expected value for E of T1 Z1 multiplied by E expected value for E of T2 Z2 all the way to that Zn. So this is just one of the properties that when you have the sum of the independents, you can write it as the product of the individuals. And now these it just reduced to the scalar version for the homogeneous function. And then what we showed earlier for a scalar version, the homogeneous function is E1/2 T squared. Right. This is for Z follow a standard normal, a scalar version, or a univariate distribution. So it also applies here. So this one is just 1/2 T squared multiplied by E of 1/2 T squared all the way to E of 1/2 T squared. And then you just have let me think how I should put it to make it easier for okay, so how about I write it here? So you will have lots of T squared adding together. And then, as I mentioned here, inner product is just a summation for the individual products. So here I'm going to use it the backward. So we have a summation of the T squared, or T multiplied by T. And then we can rewrite it as T transpose T. So I'm going to use it backward. Right now we have the summation of n things, which is written as a T squared. And then I'm going to write it in the matrix vector, or this notation here. I'm going to use it in this way, so that you will have the E1/2 T transpose T. Okay. It just, when you go into higher dimension, people using this vector notation, and then you will use this T, like transpose notation, to replace this summation. That's the only difference. So there's no other difficult things here. It just, when you go to the higher dimension, you just use transpose this T to replace this summation for n times. That's the only difference for notational wise. But at the core, it's just sum of lots of things for the inner product. Yeah. Okay, so let me clean up things here. Okay, so we have 20 minutes, so okay, then I would like to conclude on these things. So what we have is the momentary function for a multivariate standard normal. So I would like to conclude today's discussion or lecture on the momentary function for y. And then I'm going to write y, which is the multivariate normal distribution, in the following way. Okay, I haven't introduced this notation, but I'm just going to use it for now. Maybe I can talk about more next time. So this is just the sigma matrix, the n by n matrix, raised to the power of 1/2, multiplied by z. So this is again n by n, n by 1. This is the z1 all the way to zn, and then plus a mu. So for z that follow a n-dimension standard normal distribution, then the y that you constructed in this way will follow a general normal with mean mu and the covariance sigma matrix. And then this one has the density that we showed at the beginning here. It's just this. So as you have used in the scalar version, so z is equal to mu plus sigma. Okay. Yeah, I just don't want to make it. Yeah. So this is for z follow normal standard 0, 1, and then you have the x minus mu over sigma. This follow also a normal 0. So you have been using this for a long time in the scalar version, and I'm just saying that for the multivariate case, it also stays the same. So when you have standard normal z, you need to multiply by the matrix by raised to the power of 1/2, because here you also divide it by 1/2. So this is also the 1/2 version, and then you also plus the mu here. So this is the scalar version. This is the vector matrix version. So you have been using this for a long time. Right now, I'm just saying that you can also write it as a compact form, as in the matrix form. You will get the same thing. Standardization or reparameterization. This is also the same thing that we mentioned when I talk about the generative model, when people generating graphs. If you still remember that people encoded a graph into a low dimension vector z, and then they regenerate an image, like all those dog and cat image, using this reparameterization tricks to generate the image. And this is the VAE framework, the variational autoencoder, which is the generation process. And this is the trick that they use to backpropagate the gradient in the neural network. Okay, just to circle back to our discussion last time. Okay, so that's that. We essentially have a operation regarding the standard normal. So the moment general function for a general normal can be written as the moment general function for sigma 1/2 multiplied by z plus mu. Okay. So I'm going to use this to rewrite my y. And then again, using the definition for the E of t transpose multiply by this expression. So it's going to be longer and longer, so let me use the exp notation here. So t transpose multiplied by sigma 1/2 multiplied by z plus a t transpose multiplied by mu. Closing the exponential, closing the expectation. So what I did is just replace this z here by the y, and then in that summation expression here. So that's why I read it in this way. And then we just need to decompose this one. So we have the expected value for E of t transpose mu multiplied by E of t transpose sigma 1/2 z. The random variable is y, is the z here. So the remaining terms, they are all constant. So we can write it as the constant t transpose mu multiplied by the expected value for the E t transpose sigma 1/2 multiplied by z. Okay, now I'm going to call t star as my t transpose sigma 1/2. So again, this is n by 1, but taking the transpose, you have 1 by n. This is a n by n. So you should have also a n by 1 vector. So t star is also a n by 1 column vector. So you will have E of t transpose mu as a scalar, and then E expected value for t star transpose z. Okay, so this thing here is the moment general function for the standard normal random variable z. So we can directly using this one that we get here to replace the moment general function. So e raised to the power 1/2 t transpose t. So now coming back to here, this is e raised to the power of t transpose mu. And then this is the moment general function for random variable z. So we have e of 1/2 t star transpose t star. And then we need to replace the t star back to our original things. We just make a substitution there for simplification. So e of t transpose mu e 1/2. So t star is t transpose sigma 1/2, and then this together transpose, and then another t transpose sigma. Give me 1 second. I think okay, so just to make the t star as a column vector, so maybe let me change the order here. So this is sigma 1/2 multiplied by t. So this is a n by n, this is a n by 1, you will get n by 1 vector. Okay. So again, always the matrix vector multiplication, you need to make sure the dimension matching. So the way that I previously write, the dimension is not matching, so it's not applicable. It's not valid operation. So it does not make sense. So T star is that, so sigma 1/2 multiplied by T together transpose multiplied by sigma 1/2 multiplied by T. Okay, so now here let me make another comments regarding the transpose operation. So if I have a matrix AB taking the transpose, this is equal to B transpose A transpose. Okay, so let's see if this is a N by P, P by M. So you have B transpose, this is a M by P, and then P by N. So you will get M by N on the right hand side. You will get N by M on the left hand side, but then don't forget you have a transpose, so it becomes N by M. So AB transpose is equal to B transpose A. So also the other thing I want to mention is that order always matters for matrix vector multiplication. So AB is always going to be AB. If you change the order, the dimension will not match. You will never have a valid operation. Even in coding, you will always get a error message. Okay. So I'm just going to put it out there. And then just to conclude, T transpose mu 1/2. So now I'm going to make the AB transpose to T transpose sigma 1/2 sigma 1/2 multiplied by T. And then you will have T, this constant stay the same, E of 1/2 T transpose sigma here multiplied by T. So here, this sigma 1/2 multiplied by sigma 1/2 equal to sigma of 1 raised to the power of 1, or just sigma itself. So that's why these two things becomes the sigma. So just to conclude, the moment genuine function for random variable y is going to be E of T transpose mu plus T transpose sigma T. Am I missing a 1/2? Yes. Yeah, there's a 1/2 in the front. This is the moment genuine function for y, where y follow a normal dimension n, mean mu, and then sigma matrix. Okay, so just to summarize, we first talk about the multivariate standard normal. This is the density. And then for zero vector identity covariance matrix, this is the density for standard normal multivariate case. We talk about the moment genuine function. It's nothing different than the univariate case except for the matrix multiplication. And then we derive the moment genuine function for the multivariate standard normal from the scalar version of standard normal. And then we, using the reparameterization tricks, to rewrite the y in terms of z. Then we derive the moment genuine function for the multivariate general normal with the mean, mu, and sigma matrix. And then along the way, we talk about lots of matrix vector multiplication, lots of that kind of things. And that should conclude our lecture here. Okay. Let me pause.